Hello and welcome to a short follow-up video to my AM modulator circuit. Here you can see the AM modulator circuit. I've made a video about some videos ago, so if you don't have seen this video, look up this video and then watch this. In this video I'm going to explain you how to calculate the values of the components in this circuit. So, okay. At first, this circuit has three really important parts. The first part here is this, or this whole thing. This here is the oscillator which is producing the HF for the modulation. You can see here. This here is the modulator which is modulating the HF and the NF signal. And this part here is a really important part of the oscillator. This is a LC resonant circuit, which is really important for producing the HF signal. Okay. Now let's start with this oscillator part, with the LC resonant circuit. So now I'm showing you how to calculate the values of this LC resonant circuit. For this I have to say two really important things, or two really basic important things, and these two things are that for AC L is like an open circuit, and for DC an L is like a short circuit. For AC a C is like a short circuit, and for DC a C is like an open circuit. So if this circuit gets first time voltage, then the C is a short circuit, it is jerking itself, and after the C is completely jerked, the L is discharging the C, and this goes around every time. But the L and the C has a resistor, so it gets down and down, and it gets to the point that this completely ends. So for that we need the amplifier that I've shown you before, that that this process of oscillation don't stop. Okay, with this formula, the Thomson formula, you can calculate the values of these two components out, and with this formula you just have to 1 by 2 times pi times L times the square root of L times C. You can calculate the frequency of oscillation of this circuit. Okay, and this formula is built like so. The inductive resistance of L is omega times C, and the capacitive resistance of a capacitor is 1 by omega times C. If it has the resonance case, then both resistances are the same. So we can say omega times L equals 1 by omega times C. So we are multiplying that times omega. So then we can say omega squared times L equals 1 by C. We are dividing that by C, so we can say we are dividing that by L. So we can see omega squared equals 1 by L times C. So then we take the square root of this, then we can say omega equals 1 by square root of L times C. Then we're saying that omega equals 2 times pi times the resonance frequency. Then we can say 2 times pi times resonance frequency equals 1 by square root of L times C, and then we can say the resonance frequency equals 1 by 2 times pi times L times C, square root of L times C, sorry. And this is the Thomson formula. I'm sorry if this was a bit too quick, but I can just upload videos which have a length of 15 minutes, and so it is not possible to make this a bit slower. Okay, good. And as I have stated before, this signal and feeding it back, because if we are not doing that, the oscillation will stop. So for amplifier, I've chosen this amplifier here, and this amplifier has some important basics. You also can use this amplifier as an audio amplifier or whatever. The output signal is phase shifted 180 degrees against the input signal, you can see here, it is bigger. Phase shifted means inverted, and it is bigger, you can see here. And how to calculate this circuit? For calculating this circuit, we are saying that this current that goes down here is constant, and we are saying that this current here equals 1 milliamp for this calculation. You also can say that this is 10 milliamps. I'm not sure what current I've used in the previous video, so the values of these components can be different to the previous video. We are also saying that the operation voltage equals 12 volts, and the current amplification of the transistor is 100. You can look up the current amplification of your transistor in the data sheet of your transistor. Okay, now go to calculate these things. For first, we'll say that this RE takes a voltage drop of 1 volt. This RE is for the temperature compensation of this circuit, but I'm not going to explain it, or I'm explaining it. RE is for that if the current here gets more because the transistor gets hotter and hotter and the current gets more, then the voltage drop here gets more. If this voltage drop is more, this voltage drop here on the base to emitter is less, and then the current gets less. So for this is this resistor. And for the calculation, we are saying that on this resistor is a voltage drop of 1 volt. So with this we can calculate the resistor. We say the resistor is the voltage of the resistor divided by the collector current, because this current is nearly the same as this current, and in my case this is 1 kilo ohm. The collector resistor, the RC, you can see here, is calculated by the voltage on this resistor, and the voltage on this resistor you are getting if we are taking the operation voltage, this is here, minus the voltage of the emitter. In my case we have 12 volt, minus 1 volt is 11 volts, and for a symmetrical signal on the output, we need the half of the rest voltage on this and the other half on the transistor. So we have the operation voltage minus the 1 volt here divided by 2. So we have 5.5 volts divided by 1 milliamp equals 5.5 kilo ohms. Okay, now we are going to the next part, the base resistors. For this we have to calculate out first the current of this base here, and this we are calculating by taking the IC, this current, divided by the current amplification of our transistor. In my case it is 1 milliamp divided by 100, and this equals 10 microamps. Okay, and then we are taking this times 10, so we are getting 10 microamps. This is the current that goes down here, the EQ, this is this current, times 10, because we want a really stable point on this, so we are taking much more current than this, so we are times 10. So here we are taking 100 microamps. And to calculate the RP2, we just have to take the voltage on this, 1 volt, plus the diode drop voltage here, 0.6 volts, so we have 1.6 volt on this point. So we are taking 1.6 volt divided by 100 microamps, and this equals 16 kilo ohms. So you can see this is how to calculate this resistor. And the other resistor is just, the voltage on this resistor is just the difference from the operation voltage and the voltage on this resistor, and divided to the current that goes down here. And this is 104 kilo ohms. It is not really the same values that on my previous video, because I've taken another current, a different current and a different voltage. So now let's go to the next part, the capacitors. You have to draw an equivalent circuit for the input and output resistance, and then you can calculate the capacitor. For example, the input resistance is the two base resistance connected to ground, because a voltage source acts like a short circuit in an AC in AC. And here we have the RF, this is the forward resistance from the diode in the transistor, and we have to take this times beta. Beta is the same like B, also the current amplification, And yeah, this is really important because we have a current amplification in this. So you just have to connect this in parallel, but this times better. And the input capacitance you can calculate by 1 times 2 times B times RE times the lowest frequency that you want that comes through your circuit. And the RF, the forward resistor of your diode in your transistor, is calculated by UT, the temperature voltage, which is a constant, divided by the collector current, and the temperature voltage equals 27 volts. The output resistor, output resistance and capacitance is also really easy. You have just to take the collector resistor to ground, and the RCE. The RCE is also a resistor that occurs between the collector and the emitter of your resistor, your output resistance of your transistor. And this is calculated by U early, also a constant, which is 200 volts divided by IC, the collector current. And then we have this resistor here on the emitter, which is this point here, that we are calculating this resistor by the emitter resistance. Then here we have in series the RF, the forward resistance, and then we are going to these two base resistors. And with this we are calculating the emitter resistor, and we have also the same formula to calculate the capacitor. So it is not really easy to calculate these values, but a really easy way is for the output resistance, just take this resistor. For the input resistor, yes, you also can use big capacitors, so you can do nothing wrong. So for your first circuits with this, you can use just big capacitors that are big enough that the circuit works. For example, these 10 microfarads, 22 microfarads and 22 microfarads. And now also really interesting thing on my circuit is, if you are looking to my circuit, then you can see here this here. I have taken two capacitors, and this is because my amplifier has is inverting the signal, and this circuit needs a non-inverted signal. So I'm inverting my signal like this here. If I'm putting in a voltage from here to ground, it comes from here to ground inverted out. So this is why I'm taking two capacitors, just of the inverting of the signal. And now we are going to the modulator. The modulator, you can see here, is modulating because it is acting like a diode. This I've shown you in my previous video, but the important thing on this is that these resistors you can calculate